Hello, in this video we're going to take our first step into a new topic. This is collisions. So we spent a lot of time looking at dynamics, so the relationships between forces acting on objects and how the object moves around, so that relationship between force and motion. But with collisions we get a bit of a problem because, okay, we have got a force acting on an object, but usually we don't know the magnitude of that force and we don't know how long it's being applied for. So we've got these very short acting forces. So we can't take the usual approach that we've had up until now in dynamics, where we're just saying, okay, here's a particular force, let's apply Newton's second law and then see how the motion of the object changes. So we need a new approach here for looking at collisions. So when it comes to analysing collisions, we've got four maybe things that we can use here in our toolkit. So we've got conservation of momentum. Not surprisingly, this is one of our foundational principles of physics. So when we've got an opportunity to use it, then great. Now, it's not useful for every type of collision. This is useful if we say we've got two objects that are two spheres moving on a surface that are moving towards each other, and then they collide and then they separate and they start going in the opposite direction or whatever. We might even have both of them even going in the same direction. But in this case, where we can measure the velocity and the mass of each one of the objects before and after the collision, then we're well set up for doing our conservation of momentum, because we're going to be able to do a sort of m1u plus m2, well, u1 and u2. So our initial velocities multiplied by the masses is going to be equal to an m1 v1 plus m2 v2, the velocities afterwards, if we're using u and v for our velocities before and after the collision. So that's fine. The ones where we can't use conservation of momentum very easily, or if at all, is when we've got things like a ball just hitting a wall. If the wall is taken as being fixed, essentially we're trying to move the earth by having the tiny ball bouncing off of the wall. We don't have the measurements available for the velocity of the earth before and after the collision. So we can't really use conservation of momentum in that case, because it's hard to define what our closed system is, or at least it's hard to measure everything in the closed system. But for your spheres rolling around on a table and things like that hitting each other, then conservation of momentum is a really useful analysis tool that we're going to be using. Now, you note here that I don't have conservation of energy. Now, in some cases, you can use conservation of energy, which I'll get onto when we start talking about elastic and inelastic collisions. But we don't know necessarily, without more information, we don't know where the energy is going. We don't know whether the kinetic energy is conserved through the collision or not. So we have to be wary about using conservation of energy for describing just the collision. But conservation momentum is always fine, providing we can measure all of the velocities, then we're going to be okay. Momentum is always conserved through a collision, because momentum can't get transferred off somewhere else in the way that energy can. Momentum has to live inside the objects. That's where it is. It's in the objects, and energy could disappear off in sound or heat or whatever in the collision, whereas we can't have that with the momentum. Right, and then we've got impulse. This is a new idea, which it's probably the key thing, I would say, for collisions. We're taking a step back. If you think in Newton's second law that we've been using in dynamics, we've been using F equals ma all over the place. We're going to have to take a step back to force being rate of change of momentum, something which people tend to forget about when they get so immersed into the world of using F equals ma. But remember that right back at the beginning of dynamics, and when we were looking at Newton's laws, this is our definition of force. It's the rate of change of momentum. So we've got this uncertainty in collisions of how long the force is being applied for and what the force actually is. It's not just a straight case of, oh yeah, we're applying 100 newtons to something. If you plotted a graph of force against time, it's not just going to be this flat line of we've got this constant 100 newtons. You might be getting some build up of force, some distribution here, and we're interested in, well, what is this? What is the total force that has been applied over time? What is this area here? So we're getting into integral calculus. We want the accumulation of this force over time, this variable force. How is it mounting up over time? So we can actually do the calculus of this and say, well, the integral of f with respect to time from the start of the collision at time 0 up to some time t is the integral of dp. So this is going to be our change in momentum from P1 to P2. So our change of momentum, which is on the right hand side here, our delta P, the change of momentum, is this integral of the force over time. And this left hand side is what we call the impulse. So the impulse is the change in momentum. So it's telling us something. We can still measure, as we were saying, with conservation of momentum. If we can measure this, the momentum of an object before and after, because this change in momentum here is just for one particular object, so it works fine even for this ball bouncing off a wall. We can measure the momentum of the ball before the collision, measure the momentum of the ball after the collision, and we can say that change in momentum is the impulse experienced by the ball. And then that impulse is telling us something. Well, it's telling us what the area is under this force time graph. We can start approximating that and saying, well, what is then the average force over a particular time? Because taking the average force over some time period is changing that variable, that awkward area that we've integrated into a rectangle. So we can say, okay, well, this has got the same area, so we can say what the average force acting on an object is. We can also compare impulses and the effect that would have on the motion of different objects. Because an impulse is changing the momentum, is a way of quantifying how the motion of the object has been changed. It's giving us a change in velocity is what it's going to tell us. If we've got the angle of the impact and things like that, it's going to tell us about the direction of that change in velocity. And then we're back into our world of dynamics then, where we're seeing how the velocity's changed both in magnitude and direction. So that's the idea of the impulse. This is measured in, well, we can see here it's going to be Newton seconds. That's our change in momentum. Another way of putting Newton seconds is kilogram meters per second. Of course, a Newton is a kilogram meters per second squared, and then we're multiplying it by seconds. So we've got various ways of writing down what impulse is, but it's the same units as momentum because we're looking at change of momentum. So that's impulse, which we'll be looking at quite a lot. Then we've got this idea of elastic and inelastic collisions. So this is talking about where the energy is going. In an elastic collision, we're just saying that the kinetic energy is conserved through the collision. So we can look at the kinetic energy, and in an elastic collision, we can use conservation of energy as well through the collision. Most collisions are inelastic, or at least in classical mechanics that we're going to be looking at, we're mostly looking at inelastic collisions. So we can't use the conservation of energy through the collision. There'll be cases in future when we start looking at things such as gases and things like that, where we can approximate elastic collisions, and that will be useful. But at the moment, we're mainly looking at the inelastic collisions. And these definitions here, these descriptions of elastic and inelastic collisions, bring us on to a thing called coefficient of restitution, which is usually signified with the letter E. This is also something that Newton did a lot of work on. I think he may have, I'd have to double check, but I think he was the one who sort of started all of this formally with the coefficient of restitution. So we've got this idea E, and this is looking at the speed of separation divided by the speed of approach. Now, how are those things, what do those things look like when they're calculated? Well, going back to this picture we had at the top here, if they're coming together here with U1 and U2, now we want to measure all of our velocities in the same direction. So the magnitude of the speed of approach, U1 minus U2, because U2 is going to be negative if we're measuring positive off to the right. So if they're then going towards each other, then taking off that negative number makes the speed of approach greater. So it's sort of got that consistency there. But yeah, if we're moving off to the right as being positive, then we've got U1 minus U2 is going to give us a greater number. But whatever happens, we're taking the difference in these two velocities. If U2 was still going in that direction, we want a smaller number. We're taking off the positive number if U1 is catching up with U2. So our speed of approach, we just then want to make sure, in case we've been going in the other way as being positive, let's just put a modulus on this, make it a magnitude. So it doesn't matter which way we've set our positive direction. We just have to take the difference between the two velocities and then take the magnitude of that. And that's going to give us our speed of approach. Speed of separation, we're doing the same, but with V's. So we're saying we've got V1 minus V2 divided by U1 minus U2. And providing we've taken the magnitude of these, it doesn't matter. We could have V2 minus V1. Doesn't matter which way round they are, because we're just going to take the magnitude at the end. So that's our coefficient of restitution. This is something which you really have to work out empirically. You have to take measurements of the objects that are colliding with each other in order to work out what the coefficient of restitution of the collision is going to be. This is not just a property of the materials. It depends on the shape. So you need to look at the materials that are colliding. You need to look at the shape of the objects. There's a lot of stuff going on. You've got the sort of specifics of how they're colliding. Are they colliding in line with the centers of the objects? I mean, I know they always will do if they're spheres, but not necessarily if they are other shape. If they're other shapes, they might not be in line. So yeah, what are they made of? What shape are they made of? How are they colliding? If they've got rougher surfaces, you're going to get more friction and things like that. So there's a lot of factors that need to come into play for working out what E is going to be. So you have to really measure it. You can build certain models that will allow you to predict it, but yeah, at least at our level, you're going to want to try these things out. Start off with some simple collisions and take these measurements to see what E might be. Okay, so let's have a closer look at this coefficient of restitution just to see how it behaves. So we know that it is the magnitude of the separation speed divided by the magnitude of the approach speed. And we know that that's got to be greater or equal to 0 because we've got no negative numbers kicking around. Right, so let's take an extreme case of looking at an elastic collision. That seems to be our special case out of all of this, because that's where we've got all of the kinetic energy conserved through the collision. The inelastic case is a variable amount of kinetic energy that might have been lost, so that seems to be more of a range. Elastic seems to be our special case. So if we're going to have masses m1 and m2 using these values here of u and v for before and after collision, we've got a half m1 u1 squared plus a half m2 u2 squared is equal to a half m1 v1 squared plus a half m2 v2 squared. That's our conservation of energy. We can also do conservation of momentum, which is giving us m1 u1 plus m2 u2 is m1 v1 plus m2 v2. So we've got both of those equations set up. Let's now rearrange these. If these are our equations 1 and 2, let's rearrange 1. So we've got the m1s together and the m2s together. Let's clump those together. We can get rid of all those halves. We've got m1 u1 squared minus v1 squared is equal to m2 v2 squared minus u2 squared. We've got difference of two squares in both of those, so let's expand that bit out. u1 plus v1, u1 minus v1, and then m2 v2 minus, well, I'll do the plus one first, plus u2, and then v2 minus u2. Not really mattered which way around I put them. Now let's rearrange the second equation, and again grouping our terms. We've got m1 u1 minus v1 is equal to m2 v2 minus u2. We can now, if we call this one 3 and 4, if we divide 3 by 4, we're going to get rid of, well, everything that's in 4 is in 3, so that's just going to divide out. And we've got u1 plus v1 is equal to v2 plus u2. Okay, so let's rearrange all of that a bit. We've got u1 minus u2 is v2 minus v1, and then divide through. So we've got 1 is equal to v2 minus v1 over u1 minus u2. Right, you see that looks very similar to our coefficient of restitution. So what does this tell us about E on all of this? Well, we've got this value of 1 here, so we know the magnitude of these two parts of the fraction are the same. So the magnitude are the same, and this means we're going to get the same thing for E, because all we're doing by putting the modulus signs on the numerator and denominator of E is we're just getting rid of those minus signs. So we can write these any way round we want. We're just making sure we're getting a value of E which is positive. So in this case, we know the magnitudes are the same. So whatever we do, if we put modulus signs on top and bottom, it's not going to make any difference. And if we change the order on the numerator, it's not going to make any difference either. Because if we did v1 minus v2 instead of v2 minus v1, okay, all we've done there is multiply by minus 1. And then we put the modulus signs on it, and that gets rid of that minus sign. So this is exactly the same as the mod of v1 minus v2 at the top. And at the bottom, we'll put in a modulus sign on that. Well, that's not going to make any difference. I mean, it might be negative, it's taking a minus sign off, but we've just taken all the minus signs off. So we're still just looking at the magnitude of these two, these two parts of the fraction. So they're still going to come out as 1. It's no real change there. So that's just getting comfortable with what we're doing with these modulus signs, really. So this is E. So we're showing here that if you've got an elastic collision, then E is equal to 1. So yeah, if it's elastic, E is equal to 1. Anything else, well, we're not going to get that. If we had an inelastic, a totally inelastic collision, say they've just smacked into each other and they've stuck together, so V1 is equal to V2. Well, if V1 is equal to V2, we've got 0 at the top here. So it certainly doesn't work. We've got E is equal to 0 if they've stuck together, and well, that doesn't satisfy this condition here for an elastic collision. So we know that E is 0 if they've stuck together, and that is inelastic. But anything that gives us an E that isn't 1 is going to be inelastic, because we've shown it must be equal to 1 for elastic collisions. So stuck together, E is 0. Inelastic is going to be anything which is between 0 and 1. We're not going to be able to get more than that going on. Unless energy is put into the system, the objects aren't going to be separating faster than they approach, because otherwise you're conjuring up energy from somewhere. So we're not getting E being greater than 1. So we know that an inelastic collision, E must be greater than or equal to 0 but less than 1. So we got a bit of a flavour now of what's going on with our coefficient of restitution. And this comes up in quite a lot of questions. I mean, it can be a little bit forced, because they'll say, oh, here's a collision where the coefficient of restitution is something like 0.6. And you think, okay, well, how many hours of your life have you given up in order to work out that E is equal to 0.6? But we get this in a lot of our classical mechanics questions. Okay, we can measure this, we can take measurements and work out that it's 0.6, just in the same way as we have all of these dynamics questions when they're saying, oh yeah, the projectile is started on a path of 20 degrees above the horizontal at a speed of 20 meters per second or something. Well, yeah, you try go out and measure that and get those two values, the angle and the initial velocity. Easier said than done. In theory, we can do it, yeah. In practice, there's going to be a certain amount of error around this of trying to work it out. So yeah, it's a little bit forced, but we can get close to figuring these things out. I suppose we had the same with friction as well, didn't we? We've got this coefficient of friction. Yeah, well, again, yeah, how do you know? How have you got this value? So again, this is coming back to the importance of continuing to think of physics all the time as being this empirical science. You've got to go into the world, you've got to measure these things. We don't have a theory where we can just say, okay, these are the two things that are hitting each other. This is the shape, this is the material, and we know for certain what that coefficient of restitution is going to be. We might have a decent idea based on other measurements and things, but it doesn't have to be the way that it is. So yeah, it comes back to that. We need to be investigating the world. We need to keep on looking at things. But still, that's our run through of what we're using here in collisions. We got impulse, we got coefficient of restitution, we got conservation of momentum, which isn't new in this topic. The other two things are. And then we got these descriptions of collisions being elastic or inelastic based on whether the kinetic energy is being conserved through the collision or not. And these are the things that we're going to be seeing throughout the example questions that we now start working on.